Recording in progress. Hello. Welcome. EE225E, Bio EE265, lecture N-1. Woo. Can you hear me? Can you hear me? Why is everybody nodding?
Yes, we can hear you.
Oh, thanks. All right, should we start? Making any announcement?
Yeah, I guess I also posted on Piazza, but the self-grade for the last homework is due on Thursday. So if everyone can submit that, that would be great. And I think that, and then for projects, signups will be posted soon, and they'll be next week during lecture. Yeah, that's it.
That's it?
Yeah.
What about homework 11? Is it posted?
No, we can make a quiz on B courses, maybe.
Midterm 3? Midterm 3?
Midterm 3. Yeah.
Is it scheduled already?
No, we haven't, but maybe we can schedule for tomorrow.
And then the final. Right? When
final.
is the final? Which day is it scheduled?
I have to check.
Probably Wednesday or something.
Wednesday or Thursday, I think. Something.
Cool. Yep. Yeah. A lot more to do. So you got a project and a few exams till the end of the semester. So, you know, and everything that we'll cover today is still included in tomorrow's midterm. All right. So yeah, what shall we talk about today? What do you want to talk about?
I have a question.
Yeah.
What's a stimulated echo?
Ooh, there's a homework question about it, right? Okay.
I think we had one like 2 homeworks ago where we did like simulated multiple pulses, and then a lot of echoes formed. After.
Right. So when you excite and yeah, if you have three RF pulses, let me actually show it. It's a little bit out of. You know what? I want to. Let's take it offline, Anita. I don't, that can go too long, and I really want to finish today. Let's see. But basically, yeah, you had the lab where I think you did 10 excitations with 10 degrees, and then suddenly you stop exciting, but then suddenly echoes start appearing after that. And those are coherences that are being refocused and then show up at different places and with different paths of refocusing that ends up being coherent at some point. So that's stimulated echo. Okay. So anybody who wants to talk about something today? No? Okay, let's try to do something together right now, just to prepare you. So I want everybody, when I say go, to basically tell what your plans for the weekend are, but at the same time. All right, ready? In parallel. Ready? 3, 2, 1, go. I'm gonna, no, you're all muted, hold on, you're all muted. Unmute yourself. Unmute yourself and then, okay. No, you still are not muted. Unmute, Clara, come on. All right, 3, 2, 1, go.
Getting
I'm gonna just rest, I think.
brother-in-law visiting.
All right, so we all spoke in parallel, which leads to our next topic, which is parallel imaging. And then everybody tried to decipher what people said, you know, from the recording, because it's recorded. It's being recorded, right? And we might have a special guest today. We'll see if that ends up being working or not. Okay, so let's see. So far, we've basically considered the situation where we have one transmitter and one receiver, and those are pretty much sensitive to the entire volume in a uniform way. And hold on, let me just capture an image here. Oh no, Natalie, can you raise the phone again? I'm just kidding. Anyway, so we consider just a single case of a single receiver and a single transmitter. They're uniformly sensitive to the entire sample that we have. And we are only relying on the gradients to do the encoding of the image. But something happened about 20 years ago where people realized that you could actually image with multiple receivers at the same time and, you know, digitize them. And there are huge advantages to doing that. Advantages that show up in signal to noise ratio, but also shows up in imaging speed. And that really, to be honest, one of the major revolutions of MR in the last 20 years was this, because it very quickly proliferated and many vendors have started implementing those techniques. And basically every time that you go now and get scanned, you're using this technology that we're going to talk about today, which is called parallel imaging. So almost every single scan, even the not the pre-scan, but the localizer today in most scanners uses parallel imaging because you want to go quickly through those operations. So yeah, pretty awesome. Okay. So let's quickly talk about SNR. So SNR is a scarce resource, and it must be managed very well. And you've seen that when we looked at the situation where we set a certain resolution and then we regret that resolution afterwards, but then we lost basically SNR by not setting our resolution appropriately. So SNR depends on hardware, the type of sequences and sequence parameters. And we've also seen in the class that when you look at the imaging portion, just from a sequence point of view, the signal to noise ratio is mostly proportional to the voxel size and also proportional to the number of averages, or kind of like basically the scan time, or like how much you collect data, like your A to D time, the analog to digital conversion time. And it's proportional to the square root of that. So it's linear proportional to the voxel size. Larger voxel size give you better SNR, lower resolution. More scan time gives you improvement in SNR because of the averaging effect. But it's not really just averaging. You could basically do more phasing codes, or you could do, you can open change the bandwidth of the receiver, and all sorts of ways that you can actually improve SNR that way. Okay, let's do a quick overview. All right. Okay, this is going to be several questions, and you're going to answer them. Okay, so reducing the phasing code field of view by a factor of 2. Okay. Keeping the resolution the same will, 1, increase SNR by a factor of 2. 2, increase SNR by square root of 2. 3, decrease SNR by square root of 2, by 2. or decrease SNR by square root of 2? Who wants to go? So you reduce the field of view by a factor of 2. So you can skip the number of phasing codes. What does that do?
You decrease scan time.
Who said that? You decrease scan time, sure, but that's not an answer. Like, that's not one of the possibilities. But it leads to a conclusion. Do you want to go for it, Cindy?
So it would decrease SNR.
Yeah, but how much?
By square root of 2.
Yeah, all right, perfect. So half the scan time, so pretty much square root of 2, it's kind of lower SNR because we're just spending less time collecting data and the resolution is the same. So this will definitely affect acceleration methods that we're gonna talk about, because one of the ways that we're gonna speed up acquisition is going to not, like, for example, skip phasing codes, for example. So image at a smaller field of view than the object and try to actually resolve the aliasing somehow that happens to actually create an image with a full field of view. But the fact that we're collecting half of the phasing codes, that already reduces your signal to noise ratio by that factor. And that cannot be mitigated with, like, that's a loss, right? All right, next question. Improving the resolution in the phasing code dimension by a factor of 2. And improving means that your voxel size are half the size now in the phasing code direction. Will, 1, increase SNR by 2, increase SNR, anyway.
It'll decrease SNR by 2x.
Okay, why?
Because SNR depends linearly on the voxel size of each dimension.
Right. So, okay, so in that way, delta, right. So basically delta X, or, is basically halved, right? Okay, what about though improving the resolution? It's like the voxel size are twice. Improving the, improving. Okay, sorry. Okay, fine. But then, so improve the resolution by the number of phasing codes. So yeah, basically you lose half your SNR, right? But in order to meet the field of view, how many now phasing codes you need to collect though? Like, if you keep the same field of view, you have to acquire double the phasing codes for that, right? Because yeah, like I now collect more, this part of K-space, right? So yeah, so I collect all of these already, and now I also need to collect this and this and this, right? So I'm also doubling my A to D time, right? So doubling my A to D time will improve my SNR by square root of 2. So voxel size half, so SNR is half, but scan time is twice, so SNR total is reduced only by square root of 2. Okay, so decrease SNR by square root of 2. What? You said you went like this when I explained, and now you're going, I mean, is it clear? Okay. Does that make sense? So we did this exercise before last time. Okay, so let's now talk about, now that we know things about SNR, let's talk about rapid imaging. So how do you scan faster? Well, one of the way to scan faster is just collect more k-space faster, right? Instead of collecting, let's say, one phasing code at a time, you could, for example, do an EPI trajectory or a fast-spin echo trajectory and just collect more lines, after a single excitation. So you don't have to wait till it recovers and all that kind of stuff, right? So you could just do things much faster this way. And for example, EPI is one of them, echoplanar imaging, which is a Cartesian trajectory that goes back and forth. Spirals, single shot spiral or even multi-shot spiral, but they're also much more efficient in collecting samples. You can also use fast spin echo. So multiple refocusing pulses that use the magnetization you're already excited, and it just refocuses it so you can collect more lines. And you can do, single shot fast spin echo, you could actually do like a 128 number of echoes. It's of course your signal starts decaying, and you can only do that for sequences that have, tissue that has a very long T2, otherwise you're gonna have trouble. And Shreyas though showed in his clinic, for kids, they use a lot of single shot fast spin echoes because they're very quick, 200 milliseconds, you get an image, it freezes the motion. And, the stuff that he looks at actually has relatively long T2. Okay. Or you can actually do a short TR. So like these steady state sequences, for example, they could be very fast. So that's another way of doing very fast acquisitions, right? That we talked already. Okay, so that is rapid imaging. So I'm gonna distinguish that from acceleration. So yeah, speeding that up could potentially be called acceleration because you accelerate the scan, but that's not what people mean when they use the word acceleration in an MR. Okay, so the acceleration by definition, and most people will, know what you're talking, like an MR scientist, if you tell them, oh, how much this image is accelerated, they'll know what you're talking about. Okay. And the definition will be basically collecting less phasing codes or k-space data. So instead of collecting all the k-space that you want, you would collect less phasing codes. And the fact that you do that and you try to do regular, inverse Fourier imaging, just take the inverse Fourier transform, you would get a phenomena which we saw before, this folding or aliasing, right? Because you're collecting basically a smaller field of view. You're assuming that the object is smaller than, like its field of view is smaller than what you need. You collect more spacings. So this is as opposed to doing something like this, we're just collecting the low resolution, right? That's low resolution imaging. Yeah, it's faster, but it's low res. In this case, you keep the resolution, but you lose the field of view. Does that make sense? So because you don't image based on the Nyquist criteria or the supported field of view, then you'd get this aliasing if you naively reconstruct the image. Now, if you do that for radial imaging, you still get aliasing, but this aliasing is a little bit incoherent. It kind of looks like these streaking artifacts. Or if you do a random, subset of k-space, then you could get like this noise artifacts. But the effectively acceleration by definition is just collect less phasing codes, okay? But keep the resolution. So you always go up to the highest part of k-space, but you just not collect it as dense as you're supposed to based on Nyquist. Okay, any questions up to here? All clear? Yep.
What kind of trajectory is that at the bottom? Like, if it's just random, do you still use like a Cartesian or something?
Yeah, you can. This cannot be done for 2D, but out of 3D, like if the readout direction is actually through, through that k-space, then you could every phasing code just collect a different one. So yeah, so you could. These represent basically phasing codes out of 3D, 2 dimensions out of 3D. So that is feasible. Otherwise, I mean, you would have to jump kind of like, something like this, and that will be a nightmare to implement, as well as, gradient. I mean, it's too long and it's really not gonna be fast. Okay. Although every single time there's people who try to do something like that. I don't blame them. Somebody will get it right though, at some point. Okay, so here are the consequences of, okay, so a few things about this. So yeah, acceleration is great. So you can speed up, but how do you speed up? Well, let's just assume now that I can take this image, this one, that was aliased, and for some reason I can kind of unfold and resolve whatever was overlapped. Basically here, there's 2 pixels from the image, there's our original image that are overlapping, right? Let's say some oracle gives me a good way to be able to separate them and, unfold this image into a big one. So, okay, so now I have the right image and I was able to scan faster. Okay, what are the consequences of that? Okay, let's talk about that. So first of all, if you do that, then actually there's less artifacts. If you can scan faster, then you're less susceptible to motion, right? Like if I scan for 1 minute or 2 minutes, what's the chance of having motion? Half probably if it's uniformly distributed, right? If like some motion could be uniformly distributed, like can happen anytime. It's like half the probability of having occurrence, but it's actually more than that because often motion doesn't occur in the beginning, it actually happens at the end. So if I can, finish things quickly, then I'm actually better off. The other thing is, here's an example of fast-spin echo blurring. You remember that I said fast-spin echo? Fast-spin echo, you're sensitive to T2 decay. And because you got T2 decay while you're collecting K-space lines, then that causes K-space to be weighted and by T2, and therefore tissue will be blurred. But if you can traverse the entire K-space twice as fast, then you're less susceptible to that blurring, right? Like your blurring kernel is going to be much smaller, right? Because instead of, let's say, 200 milliseconds, now you finish it in 100 milliseconds. So the spins have not decayed as much as they would after 200. So here's an example with no acceleration with fast-spin echo, and here's with acceleration. And the difference between these two is that the right image is much sharper than the left image. Okay, there's less blurring occurring, which is good. Less T2 weighting also, right? Like there's much more T2 weighting here because we basically got to the center of K-space faster. However, you got new artifacts because if you can't unfold this aliasing very well, then you might end up with some residuals that are left. Okay, so this image was, let's say, fully aliased like this, but let's say some oracle told me how to unfold it, but if I can't do that perfectly, then I'm going to get some of the results left, and it's going to be a new artifact. Okay. The other thing is that from an SNR point of view, can you hear me? Can you hear me? Yeah, I'm sorry. My phone starts grabbing my headset all the time. Greedy phone, Apple, bad Apple, bad. You're a bad apple among the bunch. Bad apple. All right, so SNR. Now, SNR is a huge consequence, actually. Turns out you could have less SNR because you basically collect less data, right? The other one is that you have to apply some reconstruction, right? Like to be able to unfold those images. And so you have to apply some reconstruction, and maybe you can actually lose SNR just because you're trying to invert the system of equations that we're going to talk about later. And that inversion has some ill-conditionedness to it and will amplify noise. Okay, so that could be a result of the reconstruction. Now, sometimes though you gain SNR, and that's kind of weird. Like, how would somebody gain SNR from speeding up? Well, that's because in particular, this case, if you think about it, your signal would have decayed while you reach the center of K-space. So, you lose SNR because of that, because your signal is decaying. But here, because we're doing faster, then our signal is actually higher. So, that's certain situation where you can actually gain SNR, but you gain SNR not because of the acceleration. It's just because things are faster and, it doesn't decay as much. So again, like everything, it's complicated and depends, right? Who's the it's depends group? Raise your hands if you're the it's depends. I see one member of it depends. KT, I think it's it depends group. All right. Okay, so I actually talked about this a little bit, right? Because we talked about MRI coils, and I gave you some kind of an overview that's actually more extensive than what I was going to talk about. But basically, you can think of MRI coils as these near field antennas that receive the MR signal. They're designed to be resonant at the Larmor frequency, which maximize the EMF in the coils. And there's many different designs, like volume coils or surface coils, but often they appear in arrays of these elements. And there's a good reason for it. And the reason is because if you actually make a smaller coil, then a smaller coil has, while it has less penetration, so the field of view is smaller, it also picks up less noise. Like, the entire body generates a lot of noise, and if you have a volume coil, it will be picked up by the coil as well as the signal. But here, the signal is picked up only from this area, but also just the noise from this area is being picked up, not noise from here, far away here. And so there's just less noise to pick up, and hence the SNR is higher. Now you lose field of view, right? Because of this locality, right? Like SNR is high here, but you really can't see what's going on far away from the coil. So that's one of the issues with those, if you just use a single surface coil. But instead of using just a single surface coil, you could use an array of surface coils, right? And that's really the key. So if you actually image with many coils, you both get the SNR gain, and you gain back the field of view that you've lost because you're imaged with a single receiver. And this is an example of a multi-channel, each one of these is an element, right? So you can kind of see, like this is a loop, there's probably a loop here, another one here, another one here. So there's many loops that would receive the signal, from the MR. This is a 8-channel, for example, head coil, and you can kind of see how these are, around a head. And each one of them has its own receiver chain. So that's the key, by the way, that you don't combine the analog signal together, but you digitize each one of them separately. And that's a key. Now, so you gain a lot of SNR by imaging with multiple coils, but as it turns out, you also gain speed. And this is really what we're going to talk about today, is how you gain speed. Okay, because SNR, and here's also the beauty about it, because what do you do with SNR? Like SNR is, it makes nicer images, but at some point it's just too good. So what you could do then is, if you have high SNR, you could maybe increase the resolution, right? But increasing the resolution costs you scan time often, because you need to collect more phase encode, right? But if there's an ability to actually, reduce the scan time, and thus reducing maybe SNR, but then, keeping the SNR the same because you're now speeding up, you gain from, the multiple channels, now you can speed up the acquisition, right? So that's a nice trade-off because you can then, finish the scan faster. So we're going to talk about that. These are just examples of different arrays that people have built. This is the 8-channel cardiac coil. That's an 8-channel head coil. That's a 32-channel soccer ball. That's the one that we have in the Siemens suite. This is a 16-channel interior coil for a body, and often there's another 16-channel embedded in the table. That's an 8-channel breast coil, and this is kind of what you can see inside kind of this type of design, only this is 96 channels, and here you can kind of see all the elements. And you see how many cables, right, that needs to come out of that thing. It's pretty much a monster, right? All right, I wouldn't want. I mean, I do not envy the engineer that designed, design a 96 channel coil. I mean, it's painful. Okay, so so far we assume that basically the coil sensitivity is uniform, but if you know, each one of these coils, each one of those loops is going to have an amplitude and phase sensitivity throughout the volume that really kind of follows I lost that equation. Law, your Biot-Savart law, kind of. Not exactly. At very low field, it follows exactly the Biot-Savart law, but you know, it changes because, you know, when you put a head inside the coil, you know, it loads the coil, it changes it, so like it's a little bit more complicated. Okay. And especially as you go for higher field, there's also dielectric effects and all that kind of stuff, but approximately follows the Biot-Savart law in terms of the sensitivity. So if you actually image, you know, so if you have multiple channels, what you do is you just do gradient encoding, you know, the same, you know, 2D DFT, right? Like you acquire one phasing code, another phasing code, another phasing code, another phasing code, and this would be case-based. But then the receiver, because you have, let's say in this case, 8 coils, you have 8 receivers. Each of these 8 receivers receives an image, and that image is encoded using the gradients. So one set of gradients, you know, that you apply, and then you have many receivers that will give you a signal. Then you take the signals from each one of those receivers, take an inverse Fourier transform, and then you get 8 images. This is the image obtained from the data obtained from this coil. Okay? So it's more sensitive to the back of the head. So the back of the head is more illuminated. The front of the head is far away from the coil, it's less illuminated. This one, you know, it's more sensitive to the top right of the head, right? So this part is more illuminated. And the hope is that, you know, throughout the fact that I have this coverage, I can take those 8 images and combine them in such a way that I'll remove this illumination. I will get kind of a, you know, constant amplitude, but with higher SNR everywhere. Does that make sense? And that sometimes happens. And so by definition, what we're going to do is like S gamma. Gamma is basically either coil 1, 2, or all the way to coil N at particular R, right? So that will be a sensitivity of the coils varies in space. And the sensitivity varies both in magnitude, but also phase. Phase varies as well. So this is one of the sources of phase is actually in those receiver coils, okay? Because, you know, it really depends where a spin position is with respect to the coil. It might pick up, you know, what might induce current in the other way, right? Like it really depends. So that's or the phase that, you know, whatever spin that is spinning here, you know, it will induce a current with a certain phase at the coil, and that depends on the orientation and geometry of that coil. Okay. So what happens when you image with multiple coils? So this follows a very famous paper from Pete Romer from 1990, the NMR phased array, and I highly recommend reading this paper. It's really a classic. It's one of the fundamental papers that has been in the field of MR, and it deals with imaging with multiple channels. And it looks at the hardware of it, but also what do you do with the data that comes out of it? Okay, because it's not trivial. I mean, like what? Okay, so I got these like 8 images. What do I do with them, right? There must be some way to optimally combine them somehow, right? I mean, there's trivial ways, and then there's maybe an optimal way, and you know, those depends. Okay, so if you actually look at what is the signal that we pick up at a particular coil, right? So the signal at coil gamma as a function of time is pretty much the magnetization of the image multiplied by this spatial sensitivity of that particular coil. So just to illustrate, you know, this product here could be, for example, a brain image that is more illuminated on the right, and it's, you know, more dark, you know, on the sorry, more illuminated on the left and it's more dark on the right. Like an image, you know, like this one, okay? This is M times S, okay? M is the brain, you know, without illumination, you know, constantly illuminated, proton density. But M times S is this image. And this image is Fourier encoded. Does that make sense? This image, that the weighted image is Fourier encoded by the gradients. Okay, so you travel in K-space in this image, the illuminated image or the weighted image. And in addition to this, you've got yourself the entire noise from the body, you know, the entire noise from the entire body, but that is also weighted by the sensitivity of the coil. So you can kind of see that because this weights only parts of the noise, then this is less noise. Right? Because now this is not uniform across the entire volume. Hence, this times this is always less noise than just N sub gamma. Does that make sense? So this is one of the reasons that you get less noise, because the sensitivity, yeah, it affects the image, but it also affects the noise. Okay. Okie doke. Now, here's something. Okay, so then you can say, you know what? Sure. So each sample here, each measurement at every time point is going to have some, you know, K-space value, like some K-space measurement. So let's say this is my K-space and I'm traversing K-space. So at a particular time, T0, I'm going to collect this sample in K-space. Okay. This is a particular time. This is time. At time T0, I collected this K-space line. I'm also collecting noise, right, at the same time. So this K-space line is corrupted by noise. And this is the noise, right? So what I will get is I will get some signal, which is, you know, M times, you know, whatever. I'm going to get a signal and an additive noise to it. Okay, an additive noise. So for a single channel, you know, how I can characterize that noise? What is this noise? I can carry it, I guess, by its distribution, right? And what is this distribution? Speak up, unmute, speak up, or speak up, then unmute, speak up, then unmute, and then speak up again. I mean, that's the two options that you have.
Should be Gaussian, right?
Yeah, it's bivariate Gaussian, right? So it's an IQ measurement, so in phase quadrature, bivariate Gaussian, right? So every sample, and so you can characterize it pretty much by its variance, right? Because these are independent, you know, the real and imaginary part are independent, so pretty much it's characterized by its variance. Okay, so now what happens when you have multiple channels? If you can imagine though, look at here. Yeah, this coil observes this volume, right? This coil observes also parts of this volume too. Let's say, let's pick this, I don't know, green coil over here and the red coil over here. They have some overlap in what they see, right? So obviously, even the noise that they pick up might be correlated, right? There might be some correlation. The other thing, they might be also coupled. So some of that, you know, currents that flow over here may couple and also induce currents in the other one. So that coupling could also means that, you know, whatever one coil sees, the other one also sees, but they don't see exactly the same thing, but they see different things, but there's some overlap. So might be some correlation between the measurements that you have between these two. Okay, so coils are coupled and hence the noise is actually also correlated. So normally N sub gamma is going to be normally distributed with zero mean and sigma square variance, right? That's great, but there's actually a covariance matrix when you image with multiple channels. Because if you actually look at the expectation between noise in coil I and noise in coil J, they might not be zero, right? If the covariance matrix could be identity, in that case, everything is is independent, and that's fine. But that may not be the case. There might be some off-diagonal element in terms of this this covariance. And so this is described by a covariance matrix, which is going to be n by n, that describes the noise statistics for that data being collected. And you can estimate the sample, the covariance matrix by a sample covariance. You can collect noise data and then estimate the covariance matrix from the noise data using standard methods, like you would estimate a variance, right? Like it's possible to estimate then the covariance. And so noise for multiple channels is actually still normally distributed with zero mean, but it has now a covariance matrix as opposed to just being a variance. Does that make sense? Now, okay. So here's an example, by the way, from
Nikki, can I ask a question?
Yeah.
On that previous slide, we're discussing this in terms of looking at a case-based real or imaginary channel, or
no, the noise that comes in, noise that you pick up from each coil, right? Let's say there's no signal coming. Let's say you're just receiving now, and you didn't excite, and you're just receiving noise.
All I meant was we're definitely not considering looking at the magnitude image, right? Because there's no
we're
zero
not looking
mean
at
in magnitude. There's
we're looking at
Gaussian in a
this
magnitude
is raw
image because there's no.
This is raw case-based data.
Yeah, that's right. Okay, that's all I wanted to make sure. Okay.
Yeah. So the raw case-based is now. If you take an inverse Fourier transform, well, because it's unitary, then it will still be. You actually don't change the statistics by that. If you take an inverse Fourier transform, that's still going to work. But if you take a magnitude operation, well, then that's a problem. Okay. All right. So this is from a paper, I think, from MGH, and this is a multi-channel array here. There's a lot of things here that are done here, but what I really want to show here is, first of all, the SNR maps. So signal to noise ratio maps when you have 24 channels, when you have 32 channels, and we have 128 channels. And you can kind of see that with 128, you get much more SNR, in a very vast region of the image. Like anything outside of this circle is higher SNR than using less coils, right? So you don't improve the SNR necessarily in the middle of the image, but you improve in the periphery significantly. And we're talking about, the red here is 15,000 times more than I think a body coil image. Like if you have a volume coil that's uniformly sensitive, then that is, huge, huge improvement in signal to noise ratio. And you can compare against these three, right? So obviously more channels gives you, to some extent, up to a certain amount, will give you better SNR. Now, in addition to SNR, what often people collect is what's called noise correlation matrices, where pretty much they evaluate this noise covariance. And you can kind of see that there are some non-diagonal, first of all, the diagonal part gives you the variance, right? It's the variance. And the off-diagonal part is the covariance part. And you can kind of see that there is some covariance element, albeit if the array is designed very well, then the energy in the off-diagonal element is going to be low. So there's going to be weak correlation. And that means that it's a good array, like it's a well-designed array. If they're very correlated, that means that these two coils almost see exactly the same thing, which could be a problem. Okay. Any questions? Okay, so here's the question then. Okay. And yeah, here's the question. let's look at the situation where we're going to try to reconstruct the magnetization image, right, without the weighting. Okay. So in case one, we're going to look at what's called a full Fourier encoding. That means that we could take the K-space from each one of those coils, compute an inverse Fourier transform, and get an image from each one of those coils. So M sub gamma. So I have, for example, if I have 4 coils, I'll have M1, M2, M3, and M4. Each one corresponds to an image obtained from a coil, and I kind of put where the coil kind of elements is supposed to be. Okay, and the question really is how to reconstruct, the original magnetization image, like without the coil weightings. What is the best way? So one way that you could do it is say, you know what? Let's think of the forward model, like what is the model that the image is acquired? So in that case, let me pick a color. Let's do a black. In that case, I have some, let's look at it. First of all, what we could do is just work one voxel at a time, right? It doesn't really matter, what we do to this, like we need to figure out how to combine those 4 voxels into one value, right? So this is the magnetization at, let's say, R sub P. Okay, this is position R sub P. Okay. All right. So what is the forward model? Well, my magnetization at R sub P has been weighted by the coil sensitivity of coil 1 and coil 2 and coil 3 and coil 4, right? Each one of them. So this magnetization has been weighted, for example, by, let's say, coil 1, the sensitivity of coil 1 at position RP. And that gave me the image M1 at position RP. Okay, which is really this voxel over here, right? That voxel is M RP multiplied by S1 RP, which gives me M sub 1 times RP at position RP. Does that make sense? Now, what about this one? Well, this one is the same M at RP, but it was just multiplied by a different illumination, right? So the other illumination is S2 of RP, right? Same position, but S2, the sensitivity of coil 2. And that gives me M2 of RP, okay? And so now you can kind of see that I can kind of build a vector out of that and put, S3 and S4 of RP and RP. And that gives me M3 and M4 of RP and RP. And so while I'm actually trying to image a single voxel, I get 4 measurements of it. Okay. Now, if I know what the sensitivity maps are, if I know the magnitude and phase, well, I can try to invert the system, like to compute a pseudo inverse, right, of the system, right? So it's 4 equations, 1 unknown. I mean, how do you solve this? Well, I mean, there's minimum variance solution for this, which is pretty much kind of a least squares, right? And so this is really the equation, right? So this is what I drew before, or you can write it in vector form and matrix form. And I forgot the noise, right? I forgot the noise part, but now I have it. So pretty much, this is the single voxel. This is the one voxel in the image that I don't know what it is. It is multiplied by n by 1 sensitivities. This is a vector which is n by 1, representing sensitivity of coil 1 and 2 at position RP. And then that gives me the values of the weighted images M sub S at R, RP. Okay, and this is an n by 1. This is an n by 1. This is a 1 by 1. And then of course, each one of these coils is also collecting noise. So I've got a noise vector, right? Which is n by 1 as well. Okay. So what is the solution for this? If you studied, I mean, normally you would think, this is a very simple situation where, in the case where the noise is completely independent, then the solution is least squares. If it's not independent, you have to include the covariance matrix in that solution. And this solution actually becomes this. Okay, this is something that you may have or you may not have seen before, but it's very similar to a regular least squares, except that we have to put the covariance matrix in here. Okay, but if you think about it, if the covariance matrix was an identity, well, then that goes away, and that looks like a least squares. Okay, like S transpose S minus 1 times S transpose times M. That's the typical least squares equation. Now, if you have a noise covariance matrix, well, then you need to you include that, and that will be the minimum variance estimate. And the variance of the result is actually determined by S conjugate, what is this? Whatever. Noise covariance to the minus 1 times S and all that to the minus 1. Basically, this will be the variance of the operation, like the resulting variance. Okay, that's how you calculate that. Okay, so now we have a good way of solving for one voxel. Well, now you can do exactly the same for the rest of the voxels and just do it one voxel at a time. Okay, but for each one of them, you'll need to use the sensitivity, the right S at that position in order to do the combination. Okay, any questions? Pretty straightforward, not too complicated. And you need to, though, be able to estimate this pretty well and then, use that in order to really solve it effectively. Although a lot of times people just ignore this and just use a diagonal version of it. Not the identity, but they actually use diagonal version with the variances in the diagonal. And that gives you suboptimal results if the coils are heavily coupled. But if they're not, then it gives you a reasonable result. Okay. Okay. So yeah, and basically for the simple case where the covariance matrix is just sigma squared times I, well then the solution is very simple, right? Actually, let me just actually derive it for you because my handwriting here is terrible. In that case, what I will get is, let's see, S conjugate sigma squared times I to the minus 1 times S, all that to the minus 1, and then S conjugate sigma squared times I to the minus 1, M sub S of RP. And that equals to, well, let's see what's going on here. So I got sigma square up here and I got sigma square here, and basically they cancel each other. Do you see that? That sigma square here and that sigma square, because this is to the minus 1, and here they'll cancel each other. So it's actually independent of the variance. And so what you get is S conjugate S to the minus 1, and then S conjugate MS at RP. Okay. Now, if you think about what is this? What is S conjugate S to the minus 1? Well, S conjugate S to the minus 1 is really the sum of squares of the elements, right? Of whatever is inside S. right? Like if of each one of those elements. So it's the sum over gamma of S gamma of RP of all the coil. It's basically the sum of squares of all the coil, right? That's what it is. Actually, a square needs to be here. Okay. So if you actually look at what it is, so first of all, this is a has to be a magnitude value, right? Because it's S conjugate S, right? And so you know, it's S1 squared magnitude plus S2 square magnitude plus S3, so on and so forth, right? Okay, what is S conjugate times MS? Well, S conjugate times MS is still a sum over gamma of S conjugate of coil gamma at position R, P, multiplied by M of gamma at position RP. Okay, so effectively what you do is you take the pixel from the measurement from coil 1, you multiply it by its conjugate, the conjugate value of the sensitivity of coil 1. And then take the measurements from coil 2, multiply by the conjugates of the sensitivity of coil 2. Take the measurement in coil 3, multiply by the conjugate of the sensitivity in coil 3, and so on and so forth, and sum those values. And then after that, you divide by the sum of squares of all the sensitivities. That's really what it comes down to be. Okay, so not too complicated. It's a very simple simple approach where, but you basically, yeah. Any questions? Okay. Now, yeah, that is the optimal solution, but often people just do the dumbest thing, which is just take the square root of basically M conjugate M. So basically this is the square root of the sum of squares. Okay, so you've got like 4 channels, you take the values, you compute the magnitude square, and then you sum it, and then you take the square root at the end. Okay, then you don't care what the sensitivity is, you don't care about that, and you just hope for the best. Okay, the result will of course be weighted by the sensitivities. If you have an area that is more bright because it gets a lot of illumination, it'll still be bright. Whereas this approach here that I showed you, this one, will actually give you an image which is not weighted, right? Because we take into account the actual sensitivities. When you do square root of sum of square, you don't take that into account. You also don't use the covariance matrix here and all that kind of stuff. But as it turns out, for SNR of over 20, you know, the result is about within 10% of the optimal choice that you do. So not a bad thing, right? So long as it's found to be adequate. But if you have a low SNR regime, or you want to remove the sensitivity, or you want to really get the right thing, then you want to do the optimal reconstruction. Okay? But very common people will just take the square root of sum of squares, and that's it. Okay, so with a single coil, with no acceleration, you collect the entire Fourier domain. You know, situation is pretty much simple, right? You have now an algorithm, very simple one to implement this combination. Although you need to know the sensitivity, right? Like you need to have an idea what is the sensitivity both in magnitude and phase. If you don't know it, well, that becomes challenging, right? Because then you can't really optimally combine them because you don't know that. So they need to be measured somehow or calculated or estimated in order to perform this optimal combination. So how do we use these multi-coils for speed though? Okay, so multi-coils coils buy you SNR, and what we're gonna do is we're gonna trade off that SNR for speed in order to reduce the scan time. Now, there's a lot of methods that people have developed and with names often corresponding to alcoholic beverages. Okay, except Smash and Sense, which were early. When grappa came, after that, all the methods have been kind of named after alcoholic beverages. So caipirinha, and I don't know, there's tons of them. So this is due to Mark Griswold that decided that that's what he wants to do, and people just followed along. I mean, we even wrote a paper which we called Spirit. But spirits are also alcoholic beverages. So I think that still works out, but just like general alcoholic beverage, right? So we kept to that convention. So people have developed approaches to do this, I guess, algorithm to do the unfolding or basically do the reconstruction. Some of them, they work just in K-space. And some of them work in image space, and some work in a hybrid space, both K-space and image spaces. You know, the one I really want to talk about is the method called Sense, because it's based on a very simple inverse problem-based optimization. And if you know the coil sensitivities exactly, then this is actually the optimal solution. So it's an image approach, and it requires the sensitivities in order to do that. Grappa is another method that is based on K-space, but you don't necessarily explicitly have to know the coil sensitivities in order to perform the reconstruction. Okay, so we're going to talk about Sense, and we're going to only talk about in 2 DFT. We're not going to talk in non-Cartesian or, you know, some complicated trajectories, just in 2 DFT. We're going to assume that the sensitivities are known, which in some cases is a good assumption, but in general, it's not a great assumption. Okay, albeit Philips, that has been, you know, one of the early, basically the earliest vendor to implement Sense, have made the estimation of sensitivity map an art. You know, they really nailed it down, so they really measure it very nicely, and they have a really nice estimate of it. So kudos to Philips for doing that. Other vendors were not that successful in doing that. So they often use these grappa-like methods that don't necessarily estimate the sensitivity maps. Now, I think this is the kind of like key figure that tries to explain like why having multiple coils actually works. Okay? Like, why can you speed things up? Here's the idea. Coils restrict field of view. Okay? If it's restrict the field of view, then your field of view is actually smaller than the object for each one of those coils. So maybe then we can just reduce the number of phasing codes and then not get aliasing because the field of view is restricted. So here's the theoretical situation. Let's say you have an image of a brain, and the image of the brain kind of, the brain, a full brain is something like this, right? This is a full field of view. Now, if you have a coil that is put in this side, this is the blue coil that is put here. Let's say this coil only sees half an image. So it really doesn't see the backside of the head. And let's say it's perfectly, 1 and then 0. It's not, but let's say it is. So this coil sees half the field of view. Now you have another coil that's over here. And I'm going to draw now a different, like the same head, but like differently probably because I can't even do anything correctly. And then this coil is located over here, and it sees the right side of that half of the field of view. So if I collect all K-space, then I would get an image that has half a head and half empty. And here I'll get an image that's half empty and half a head from the other coil. And then I'll go and I'll combine those two just by adding them, right? That would be perfectly well. Or I can just, crop this part and then stitch it to this part, right? Does that make sense? Okay, so what happens if I actually reduce the field of view? If I reduce the field of view, I'm gonna get aliasing. But because this is half a head only and it occupies half of the field of view, then the alias part actually doesn't overlap with anything. And for this case, it's exactly the same. The part that aliases it overlaps with the empty. It doesn't overlap with the signal. And so if I want to reconstruct, I will then take this image and I will stitch it with this image. And I will get a head with half the scan time. Okay? So you can kind of see now how it could have bought me that, right? Now, often this is not really the case. This will start leaking a little bit and you'll still get some values on the side, albeit not so strong. And in this case, you'll have exactly the same thing. And so you'll have some residual. If I do this trick, I will still get some residual of aliasing that I can't get rid of because of the roll-off, okay? Oh, I think I have a guest, hold on. All right, so that's the idea. So in practice though, coils don't really restrict the field of view explicitly. And so we need a way to solve this aliasing, right? And the question is like how to go about it. This, by the way, this approach that I just showed, there's actually an algorithm by Mark Griswold himself. Before he developed grappa, he developed a method called PILS, which exactly does that. It crops, part of the image and then stitches them together and, makes an image out of that. And, sometimes it works, sometimes it doesn't work as well. When the coils are distinct, it works really well. When the coils are not distinct, it doesn't work that well. Okay. All right. So this is Professor Pamir. Hold on. How do
Where's the camera?
What? No, I need to remove the background. Background filter. There you go. We have a guest.
Hello. Can they hear me?
I think they can you hear them? Can you hear him?
Yeah. Hello.
Hello.
But I can hear you.
Oh,
But
okay.
they can't.
Oh.
I can switch to this.
No, we can hear him.
What do we
But he can't. Power
Oh,
engine.
I
Do
see.
you know something about it?
A little bit.
A little bit. Okay, so let's do that. I'll still use this as a microphone, but use this as a speaker. Can you speak, Akin?
Hello.
Oh, you can't?
Oh, no.
Oh. Select speaker. Same as the system. That's the problem. Okay, that's not what I wanted. Can you speak again?
Hi. Can you hear me? Oh,
Hi.
now I have like
An echo?
an echo. Well, actually it stopped. I think now it's fine. Okay. Cool.
All right.
Please continue.
So yeah, where were we? So let's talk about k-space sampling now. If you collect the full k-space, if you just do a standard k-space sampling, you cut out all the measurements and then compute an inverse Fourier transform, you get an image. But if I skip some of the phasing codes, then my image is going to be overlapped, like like take a pita bread and just start folding it. Then this is what you get, except that it's additive. Do it again. All right.
Should I read you?
No, you can stay here. You really don't ruin my concentration at all. So here's the basic idea of parallel imaging. Okay. I got myself, 4 coils, and each coil will have its own sensitivity. This one's sensitive at the bottom, this one on the right, this one on the top, this one on the left, and so on and so forth. I'm going to undersample, and I'm going to get folding of this image because I undersampled. Okay, but the folding in each one of them is different. Effectively, in this case, 3 pixels overlap on top of each other at every single point. And in this place, 3 pixels overlap with each other, but they overlap differently because they're just weighted differently. In this case, again, weighted differently. And you know what? If I actually stare at this image, this point almost doesn't appear as if it has aliasing whatsoever, right? I could have kind of cropped, this part of the image, and I would, delete this, and I would, that looks pretty good. And then I could have did all same thing here. And that looks like the front of the head, but they're still corrupted. There's still a line over here. There's still stuff, right? But I've got, again, every time I got 3 foldings, but they're weighted differently. So effectively, I got myself 3 unknowns in this case, and 3 unknowns here and 3 unknowns here. It's the same 3 unknowns, but I got 4 equations for them. So I got 4 equations and 3 unknowns. Can I solve 4 equations and 3 unknowns? Yes. Can I solve 3 equations, 3 unknowns? 4 equations, 3 unknowns? Yeah. Well, haven't you taken this course? What's the right answer? What's the right answer in this course for any questions? Yeah, it depends. It depends. On what it depends? If you have 4 equations for an, they need to be independent, right? They need to be independent. And obviously should be well conditioned too. So yes, we might be able to solve this because we have 4 equations, 3 unknowns. But it also depends on the situation where those are actually independent. And the idea then is to take all those aliased images and then combine them in a certain way that will give me the uncorrupted image or the unfolded image. Okay, solve this folding. So let's talk about how we do that. Before we do that, let me just again kind of show you the principle of it. And I think we're going to probably do some of the things today, but not everything. So in regular Fourier imaging, I got, again, this is my signal equation as a function of K-space. It's my magnetization multiplied by the coil sensitivity. So I got a coil and I got an image, and the image is weighted by the coil sensitivities. This is the image, and I do Fourier encoding. These are the encoding functions that I use. This is, for example, one complex harmonic that I use, right? And you use different functions in order to encode this. And then the idea is that once you have an inner product with those, as you make many, many measurements, you're able then to resolve this image. Now I'm going to flip it around. What I'm going to do is I'm going to look at a different situation. The different situation is that now the unknown is actually the unweighted image, and my encoding functions are weighted complex harmonics. So in this case, when I have, let's say, 2 coils, the encoding function for the left coil is going to look like a complex harmonics that is weighted by that sensitivity this way, and this complex harmonic weighted by sensitivity this way. But I measure those 2 inner product at the same time because this is the data I'm getting from the receiver. The data I'm getting from the receiver is in parallel. And that's why it's called parallel imaging, okay? Because I receive the data in parallel. And effectively, when I define it this way, then I get two encode, like here I get one encoding function, one inner product at a time. Here I get two at a time. And this is where maybe I can use that in order to speed up the acquisition. So normal acquisition, I would first, lower case space, higher case space, higher case space, and higher case space, and so on and so forth. But in the other situation, I will get, two at the same time and two at the same time. So maybe actually I can skip this one and this one. Maybe this is enough in order to reconstruct the image. 4 measurements, in this case, obviously 4 unknowns in this brain, right? Like 4 unknowns, obviously, right? I shouldn't talk about my spouse that way. This is my spouse's brain. Is it gorgeous? Look at that. This, by the way, it's a very famous brain. It appears in many presentations of many people without them knowing that it's my spouse, because they just copied it from lots of presentations or like online material. It's famous figure. So we even had a candidate coming to interview at Berkeley, and famous candidate, by the way. Famous candidate. Now she's faculty at some other institution, but not because of the mistake that she did, by showing that image without citing actually where it came from. Like I actually saw my wife on a presentation in her job talk, and I was like, huh, I recognize this one. And yeah, that was my spouse. So yeah, famous image. All right. Okay, so previously you have one encoding per one time point, and you end up with n images at the end. Okay, so one encoding per time point, and you get n images, right? Like you do full Fourier encoding, you get n images. You have n coils, you get n images. Now we can do n encoding per one time points because we get n samples from each one of those coils, and we're going to try to reconstruct one image at the end, not n images. So we can do them faster by skipping phase encodes because we have n encoding at every time point. So maybe we can skip. Now the question is like how much we can skip and so on and so forth. Well, that depends. Okay. So let's see. We're kind of like 2 more minutes. So I think I'm going to stop here because now you have the idea. And then next lecture, we're going to basically go and develop the whole thing and actually solve it. And I'm going to leave you with this taste of, how do we actually do this? So we're going to solve it rigorously. And then hopefully if we have more time, so we're going to try to spend maybe half of the lecture doing that. And then I'm going to spend half of the lecture trying to tell you how to estimate close sensitivities, which used to be thought as a no problem till it became kind of a problem. And now it's kind of not a problem, but still somewhat of a problem, as Shreya could tell you at some point. All right. So with all of that, I think I'm going to say goodbye. And I will see you on today's Thursday? No, today's Tuesday. Oh, so we have another day in the week. That's great. So midterm 3 is tomorrow. And the next lecture after that. All right. Bye. This meeting is being